AP Physics C, Electricity and Magnetism, Current and Circuits Problem-Solving Techniques. We will start with a quick introduction to let you know how you should be using this notebook. We'll then have a summary of the presentation that was done on current and circuits with the most critical equations and just kind of like a highlight of what you should know. Then we'll go through several problems. One with 2 batteries, an RC circuit, then 2 capacitors and 2 switches, a capacitor and 2 resistors, capacitor and 1 resistor, then 2 capacitors and 1 resistor. Introduction. This is not a typical unit presentation. There are no formative assessment questions to test student knowledge. However, comprehensive current and circuits problems are solved step by step. Before you go to the next step in a solution, try to figure out what the step will be and work the problem. There are questions in the presentation which you should also attempt to answer before moving on. You can work these problems on your own, with a group of students, or led by a teacher. Current and circuits summary. The rate of flow of charges through a specific area in a segment of time is called a current. Circuit analysis will always use the flow of positive charges, even though we know it's the flow of electrons, and that's from good old Ben Franklin. And this is known as conventional current, which will be I is equal to dq dt. In the past, you may have seen it defined like this before we did the calculus representation. We'll probably use both. Another definition of current was derived, and here it is, where current is equal to the elementary charge, which is 1.6 times 10 to the minus 19th coulombs, how many of those charges you have flowing, A is the cross-sectional area that the charges move through, and V sub D is the drift velocity of the charges, which is much slower than the speed of the electric field propagation. Then we have current density, and that's just going to be current per unit area, so that's En V sub D. The resistance to the motion of the charges is called resistivity, ρ. ρ is expressed as electric field divided by current density. ρ has a temperature dependence. That's listed right here. The higher the temperature, the greater the resistivity. Where this term alpha, that's just a coefficient, the temperature coefficient of resistance. Resistivity is a micro property of a substance, so then we define resistance equal to ρ times the length of the material divided by its cross-sectional area. Then we have Ohm's law, delta V equals IR, or many times people just go ahead and write V equals IR. We're not that careful about the delta, but this does not work for all materials. If the material obeys Ohm's law, then it is an ohmic material. If it does not, then it is a non-ohmic material. The electric potential energy per charge is called electromotive force, or EMF, or this little squiggly e. This is not a force, but the name is preserved for historical reasons. In a battery, the EMF is the maximum voltage that can be delivered to a circuit. Batteries, however, wear down over time, as we all know, and this is represented by a virtual internal resistor, little r, and you can see little r right there. That will decrease the supplied voltage. And that supplied voltage is called the terminal voltage. And this black box here, this represents the battery. And if you measure the voltage between here and here, that's terminal voltage. So the terminal voltage is your EMF minus the current through the battery times the internal resistance, and then you can express it in a couple different fashions here. You treat that internal resistor, for the sake of our circuit analysis, as if it were a real resistor. The battery will deliver an electric potential energy of Q delta V to each charge Q. The rate of the energy transfer is called power. Power is I delta V, and you can also express it as I squared R, or delta V squared over R. And again, many times people just leave out the delta. Resistors can be placed in either series, so that would look like this, where they're kind of in a row here. Well, excuse me, I can't draw the resistors too well. Or in parallel, where they look like this. That's a little better. In a series circuit, the current is the same through each resistor, but the voltage drop will depend on the individual resistances. In a parallel circuit, the voltage drop is the same across each resistor, but the current will depend on the resistances. The equivalent resistance is the value of a virtual resistor. It does not really exist, but it will act the same as the resistors it replaces for circuit analysis. So resistors in series, here's how you find our equivalent, and in parallel, here's how you find our equivalent. And make sure when you're doing the math for this guy, you remember to flip your answer at the end, because if just doing this, that solves for 1 over R equivalent, but you want R equivalent. Not all circuits are simple series circuits or parallel circuits or have just one battery. In that case, we need to use Kirchhoff's rules to do the circuit analysis. The first one is the junction rule, which is the algebraic sum of the currents into any junction. And here's a junction. It's where a couple currents meet up and become a third. And the sum of those currents has to be 0. Another way of saying it is the amount of current that flows into a junction is the same as the amount of current that flows out. This is a consequence of the conservation of charge. Kirchhoff's loop rule is the algebraic sum of the potential differences in any loop. And we've drawn a loop here. The loops are arbitrary. You can draw them however you want. Could also have drawn a loop like this around the whole picture. Those potential differences have to add up to 0, and that's the conservation of energy. And let's see, this would give you a positive delta V, leaving the battery like that, and then through the resistors, negative V, okay, because what you're doing is you're transforming that electrical energy into thermal energy.